Yeah, so I wanted to provide you a short update on our work on leakage detection on building envelopes, because we've got our new test bench, so we did some measurements there. And the methods we're using are acoustic camera and lock-in. So the goal is to develop leakage detection measurement technologies that are fast and easy to use and potentially automable. Acoustic camera. So this is basically a follow-up to the presentation I gave in Leuven already. But just to repeat, acoustic camera, we've got a loudspeaker inside the building and an acoustic camera outside, and the sound goes through the cracks in the building and basically follows the same path as the leakage path goes. And with a beamforming mechanism, computer can create colorful pictures that show us where the sound is coming from, and we interpret that as there are the leakages. In lock-in thermography, we have infrared camera looking at the building from the inside or the outside, both is possible. We have a way to pressurize the building in a pulsed way. We take infrared videos, and by Fourier transforming the videos, we can determine amplitude images and phase images, especially interesting at the frequency of excitation, of course. So this is the test bench we have. Basically, it's a chamber we can walk into, which is quite airtight. And at the front, we can exchange our test specimens. We've got a fan, so we can measure the leakage rates. And then we have our measurement devices there. First thing we found out was that the sound was also going directly through the walls. So we had to do some soundproofing with some foam material. So after that, we reached significantly higher sensitivity there. One of the first questions we investigated with the acoustic camera was, what can the sound really go around corners? What if we have cavities in there? So we investigated two kinds of specimens here, a labyrinth system and a sandwich system. Both are made of back plates from wood and some acrylic glass cover plates. So this is one example with a labyrinth specimen. We have to the back, there's a hole diameter 5 millimeter. We also have smaller holes or bigger holes. And then we checked if we can still see the leak. And in this case, we were able to detect both leakages. And then we switched to smaller holes with 3 millimeter diameter. The other hole was 7 millimeter. We could still detect that one. But then we made the labyrinth longer a little bit, and then that was over the edge. So this is about the sensitivity we can reach here. So this was a sandwich system. Basically, we have several acrylic plates behind each other. And we have openings in form of slats. So the air has to go this loop path. So in this case, we were able to detect the leakage if we have a slit of 7 millimeters width, also a 3 millimeters width. So we went a little bit further, added another plate there. With 7 millimeter, we were still able to detect that. With 3 millimeters, not anymore. So with 7 millimeter, we went a little bit further, and that was again the sensitivity that we could reach there. Okay, we also did some measurements with the lock-in measurement system. There, we wanted to investigate if inverting the pressure would also give us some additional benefits. So we started out with, we just switched on and off the fan. So we only worked in pressurized and zero pressure. So we went to an inverted system where we pressurized and depressurized. So the idea came from the question whether with the stack effect we would have some pressure bias, and maybe this will create some problems there. On the other hand, one would expect factor 2 improving the signal, which is always good without having to increase the pressure. So we did a small study here. In that case, we had the fan running continuously, creating a pressure of 50 Pascal. We had a valve switching system that was able to switch the pressure quite quickly. Temperature difference 10 Kelvin. Infrared camera was running at 2 Hertz. We investigated 3 periods, 10 seconds, 40 seconds, and 160 seconds. So, for example, the 10-second period is 5 seconds pressurized, 5 seconds depressurized. Always evaluated 3 periods. All the measurements were preceded by a preparation time of 5 minutes depressurization. For your information, the camera was about 4 meter in distance. So with the optics, 1 pixel is 3.4 millimeters. So the main idea was to compare what happens if we switch from inversion to without inversion. The specimen we investigated were Z channels. The material was medium density fiberboard. Basically, it's 2 boards screwed together. In one board were holes, in the other channels and the hole. So the air does a set form path with diameters 3 to 8 millimeters and length up to 500 millimeters. For the evaluation, so down you see on the left-hand side the amplitude image. Already we have to zoom in a little bit. We see in the amplitude the boreholes with the end of the Z channel. In order to compare the amplitude to the noise, we also evaluated 500 pixels to do some statistics. So we determined the threshold where 66 to 95% of the amplitudes were below that. So this should be the threshold of detection. If we zoom in even further, we chose the pixel with the highest value. Usually in infrared temperature measurements, you say you would need at least 3 pixels. We went below that because we want to go to the edge of detection. But if you compare only same with same, I think it's okay. It would increase the noise in the graph there. But the graphs give quite consistent results, so I don't think this is a big problem here. So here are some selected results. On the left-hand side, you see the amplitude of the detected temperature variation plotted versus the period of excitation. In that case, for a channel of 32 millimeters in length, the dashed line are always with inversion, the solid line are without inversion. And of course, you see with increasing period, the amplitude also increases, but waiting much longer doesn't really increase the amplitude that much. What's quite interesting that the signal increases by about factor 2.4. So it's even more than 2 times the signal in average of all these measurements. So it's much, if you want to do a quick measurement, do the inversion, and it's much better than waiting for a long time for long periods. A very similar result we see with the long channels. You also see the dotted line, which is the noise. So for almost all of the measurements, we were above the noise level. Here are the plots, amplitude versus length of channel. I was afraid that with the longer channel, we might lose the signal and might not see anything. Interestingly, a channel length of 0.5 meter, we could still, in almost all of the channel types we investigated, we could still see a significant signal, although it went down a little bit, but not as much as one might expect. Okay, so conclusions. We did some first measurements with the acoustic system and the lock-in measurement. We could show that complex leakage paths were able to detect with the acoustic camera. For the acoustic camera, the next steps will be, we want to work further on suppressing interference signal and increase the automation. And for the lock-in thermography, next steps will be, we want to develop a live tool, so we don't have to run an evaluation script, and we also want to do more complex mockups. Thank you.
Thank you.